I'll share again. Now is it showing it or not? Well, what the hell? It says it's, let me try, I was trying to share, I'll just share the whole screen, see if that goes. Did that go? Yeah, I was trying just to share the window because I've got this widescreen monitor. It's probably hard to see the whole thing, but anyway. All right, so here's the problem statement, as simple as it gets. We had done this project. Get rid of this thing. While ago, right? Where I want I wanted to look at the feasibility of using decision trees to just sort of automate the whole process of all of them so that we don't have to click through all the bullshit, right? And in order to do that, I've got these lists of wells that I made back when where we had all the CMR data. So we needed to have like calibration standards, right? Every single one of these wells in this database has got NMR. And NMR is sort of like it's like you walk down the street, you see a guy with a Rolex, right? It's the Rolex. It means he's probably got other things that are nice too, like a Mercedes or whatever that goes along with that Rolex. So, these wells, they've got ECS. Uh, some of them have dielectric data. Some of them have other advanced logs that assist in calibrating. So the idea was let's clean all of these things up the best that we can and then train some models to predict the data. And then we'll do an assessment, like a quantitative assessment on how well the models predicted the data over the entire data set and where it failed and how it failed and why it failed. So I had P&P go through these wells, create a new set of tops called tops underscore ML. And the idea was the mandate that I gave them, you do not put any training data in the system unless it's actual recorded data of high quality. So if there's like, in this case, there's a casing point down here. You see this? Caliper goes from 10 inches down to 6 inches. So there's a hole change there. There's missing data. We did some sort of regression work to patch that in, but we don't want to include that in our training data set. So there's a gap in our tops there. Now, the primary focus obviously was looking at this Permian section, but you've got all of these other, formations that are part of this thing. So, when we look inside the wells, we'll see, for example, here we've got a huge ECS data set with all this elemental spectroscopy, weights and dry weights and volumes and bullshit. But ultimately, I can see if I plot my Eland dolomite volume, right, that it's like 95% dolomite in the Devonian. Well, the problem that we have in this particular well is that we ran a mineral model that's got quartz and calcite in it that are so indistinguishable that it's putting them in the model instead of porosity. And so we need to come into all these wells and fix all this stuff so that it's not all fucked up, right? Like these were not primary objectives at the time. So how do you do that, right? You create a second model in mineral salt. Okay, so I've got like this model 1, model 2 thing, and here's where I have my mixings, mixing 1 and mixing 2. Where the mixings I assign models based off of whatever cutoffs. Otherwise, it's just defaults to the second model for the whole thing. But so for my model 2, I'm not even using it right now, right? Everything is model 1. So I can come in here, I could say, well, I don't want this shit, right? Just gonna get rid of it. And then I can come back over here and take my Devonian section, which is actually like really Ellenberger. And the Devonian, to be fair, right, a lot of times it does have chert in it. So, you know, maybe somebody just didn't know, but let's just do that and rerun everything. Boom. You know, now I've got porosity, now I've got dolomite, but I've got way too much dolomite. Right? It's like this, there's and way too much porosity. So something's not right about that either. I need to think about my model. Like maybe I should put calcite back in. If I do that, then now it looks a little bit more reasonable, you know. And if I look at my my QFM volume on my ECS, I actually have no lime, but I do have quartz. So if I just kind of do that, now I'm matching my quartz from the ECS. I'm matching my dolomite. This is the right answer. This is what I should have. And this sort of matches the, you know, the chert in the Devonian. So I got my chert, got my dolomite. I don't have limestone causing a problem for me. This well, you know, is now kind of passes the sniff test. The other thing that we kind of need to do is we have to look at some of the clay interpretations and other things that are sticking out. There's a couple of different, you know, interpretation formats that we can look at. There was that one. There's like this ML model results thing where you've got all these different models that were, and what we're playing with here is looking at the difference between, you know, depth shifting and raw, like what the impact was overall. So we had different objective than we've got now, which is coming in here and getting everything correct. So this is a good little exercise for you because you get to, you know, play with everything. And, you know, we've got quite a bit of calibration data, POC and stuff. I mean, keep in mind too, like these ELANs, this is a conversion that is run by Schlumberger. This is not the answer. It's another interpreted product, but it's usually pretty accurate. So like before we had all that limestone in here and everything was sort of weird looking, I think I like this answer. We've got better now. And then the other thing too is now I can come in here, I can see the differences, you know, and I can also look at the error. So, you know, there is quite a bit of error in this model, and the error is coming from the fact that I've set specific boundaries on inputs, and based off of the boundaries that I set, you know, it decided to put the error in there because it said that you told me I needed to match. In this case, it's the PE curve that's kind of blowing up. It says you told me I needed to match this within a certain range, and I wasn't able to. Therefore, you've got this total error column with the red bar in it. It says I failed you. I wasn't able to do what you wanted. To fix that, you've got a couple options. One is I can come in here and make that much more wider tolerance. So now the error goes down and it puts a lot more quartz in because I allow it to. But now you can see my quartz volume is much higher than what was previously computed, and it doesn't match the ECS. So it's not that I want to let the thing run wide open with no constraints. I want to tell it you need to match this within some number. However, something still is messing with. So if I get rid of pyrite, it really kills me, right? So I got to leave that in there. So really what I've got left now to mess with are if my U is too low, I can either change the U or the density. So like what if I put 2.92 in here? It adds more error and it adds more quartz because it's trying to maintain the same grain density, you know? So because the rock got more dense, it had to change it. So if I put this back down to 2.85, I'm gonna see less quartz now. The U is getting closer and everything's sort of going in that direction. So now, you know, I don't know why the quartz, and I change that a little bit. It's even getting better yet. Maybe if I change the U on the dolomite down to 8, okay, now I got a problem, right? Change it up to 10. Now I don't have a problem. So, you know, does this answer down here make sense? You know, I'm basically kind of matching the quartz. I got my dolomite volume right. My porosity is not wild. No limestone. Oops. I don't know what the hell just happened there. No, I guess I lost that guy. There's no limestone and no clay, right? So like everything sort of jives here. I'm just going to save it, right? That well, as far as I'm concerned, looks pretty good now. We fixed the problem that we had before. Now, like to the rest of this dolomite, if it's not that bad, don't worry about it. Wolfcamp D is pretty bad. I got quite a bit of it in there. And I see some differences between the clay volume from the ECS and my clay volume. And I also see significant differences in pyrite, which is probably what's driving a lot of that. So, you know, again, different ways of doing this. We can change the clay density. If I come in here, like we were talking about before, and I look at the Wolfcamp D, say, well, gee, look at that. Somebody picked the 2.56 for the neutron clay density. I could probably do something like that, right? And if I were to do that, and then I rerun my clay parameters program, and then rerun mineral solver, it changed it, right? My porosity still isn't bad. I got rid of more of the dolomite. So clay volume came down, which now matches the ECS a little bit better. Like, you know, without having to put that ridiculous 7% of pyrite or whatever in there, I was able to kind of get a little bit cleaner. Wolfcamp C, let's look at the same thing. This is a more difficult one, right? Because you're going to say, well, gee, this is a good pick. But again, if I do that, okay, now on the porosity side, I'm a little bit high in some of these intervals, and I'm a little bit low on the clay. And if you look at what's happening there too, like all of these should agree kind of. So it's that density endpoint that's sort of, and the sonic endpoint here, which could be 130, usually is in the Wolfcamp C. So like that sort of matches my neutron density. I'm liking what that looks like. So again, I kind of rerun that. I'm just going to live with some of these little blips, I guess, and not worry too much about it. That looks a little bit cleaner. All right, Wolfcamp B, same story. I come into the B, right? Maybe I need to be down there. Well, if that's where I am, dolomite's gone. Now, we have a problem when we're doing this, right? Now we're getting porosities that are too high, and our clay is too low. So, you know, now I got to look in here to see what happened. Change that, you know, somewhere in here. Okay, I got that kind of lined up. There's some depth offset issues in some of these wells too. You can kind of see it so that they weren't depth shifted properly. That resulted in some of these things like here too, right? Just making sure that my gamma ray is not throttling anything. Back to our plot. Can we live with that or not? I don't. Seems like we need more clay, and that would kill that porosity. But the only way that we can do that which we don't want to do all the time, but we can come in here, we can do this. So now we had this other Wolfcamp B look like that. This Wolfcamp B looks like this. So now we may move that up a little bit, right? That's going to give us that more clay that we weren't getting before, that little extra zone. So now this kind of screams to the problem too of needing to do this very top of that B there, needing to do this in a different basis than how we currently are. But really, it's just up there, I guess. Where we going? So we fixed it up there. Now it matches perfectly. I guess I missed it. What did it go down to 87.22? So it should go down to here. Where we going? So yeah, that's fine. The other thing too is you can see some of these low zones, like the Sonic is throttling it. So you move the matrix endpoint over a little bit and it'll line up better. Boom, fixed, right? So unfortunate, something happened there. It's a little bit different in the clay world that we have to account for, but once you got it accounted for, fix it. Wolfcamp A, I'd probably just leave it. Or if anything, maybe do something like that. See how much that makes a change. Got rid of most of the dolomite, you notice that? Just that small change. So you can kind of continue this process through most of these intervals. And some of this stuff, you know, there is legitimate dolomite in here. There's heavy minerals that you're seeing plot along this dolomite trend line. But you know, these little refinements make a difference, especially this stuff at the bottom here. This was a massive error, you know, to not have that fixed. So, you know, stepping through these wells, you're going to see like this Clear Fork interval up here in the Ackerley Nichols 19. This is all fucked up, right? This should not look like this. Now we've got dolomite. We've got 4 points. They're all 0, pretty much. So this dolomite should not be in it at all. So something's wrong, you know. And here, let me. That's the only problem with IP2 is once you start this shit, look at the windows, right? So many fucking windows, you can't keep track of all of them. So what's going on here? Clear Fork. That guy. The first thing I can see that the gamma ray is too low in a lot of it. So changing that down, don't let the gamma ray be a constraint, you know. And the second thing I can see too is that the sonic data probably needs to do something like that and something like that, maybe. Let's to kind of move that around. Then we got our neutron density data. What are we going to do with that? You know, to kind of look at some of these things. There's depth offset issues again. Some of these aren't perfect. Seems like neutron density is the lowest. So just with those changes that we just made, which were not very much at all, can we get this to move at all? Shoved a bunch of fucking porosity in there, that's for sure. By doing what we just did. So bulk density is quite low. POC volume's about right on. Our grain density is way too high. So why is our grain density so high? Coming from these things. Pyrites on. Try messing around with some of these things, right? What's going to happen? I lower that, brings my grain density down, but then it's putting more of that in there. That's what's less. Maybe my quartz is too high. So this is a toughie here. There's something going on with this data and a pretty good hole size too. Something going on that's just odd. And it could be that this is legitimately dolomite, but we're just missing it with the plug points. I don't know. I have a hard time believing that. I think there's something else fundamentally wrong. It could be clay. You've got some leeway to play with these things. That comes back to that solver, right? The solver program. There's the 7H there. Oh, I'm sorry, the acrylic necklace. For that thing. So did the program here solve it a different way? It did. Got rid of the dolomite for the most part, but matched everything else. So how did this do it? So there you go. So for the clear fork, it's using .66, which is basically what we've got, and 0.56. So it's putting the neutron endpoint a little bit out further. About right there. Okay. For the minerals, it's saying that our quartz is actually 2.69, which ain't that much different. Saying the PE at quartz is 2.18. So 2.18 times 2.69 is 5.86. These are minor tweaks, right? 2.74 for the calcite, which is quite a bit different. PE at calcite is 5.33 times 2.74, which is a 14.6 for that. Dolomite is about what we got. And then all the rest of this stuff, I think it's pretty much doesn't matter. So if I rerun this now with those matched parameters, I still have dolomite in the model. Something's busted. Something isn't right. Okay. And sometimes when this happens, it's because the mineral solver itself is bugged out. And this does happen every now and then. So what you have to do, we'll save this to that well. Okay, and then you come up here and you go to here. You look for mineral solver and the acrylic nickels and you delete it. Yeah, on. Now you come back in here and it's going to start scratch, blank, nothing in here, right? So load my parameters. Oh, I'm not even going to load that saved one. I'll load the saved one. All right. So, does it maintain all these things? I don't even know what's going on in life. But, okay, rerun this. Get the same result by the looks of it. Didn't change anything. And that's odd because it should have. So let's try this. Delete that thing again. Rerun the mineral solver. Okay, now I'm just going to load in the default mineral solver thing. And then I'm going to load it on top of that, my tops. I don't like the tops either, but whatever. I don't like when it's all picks usually. So you kind of just start this thing from scratch. And we'll see what happens. So now you run that. Now it changed. Look at that, dolomite run. That's interesting, right? And now there's a whole bunch of it here. And okay, at least like there's something bugged out with that mineral solver model for whatever reason, or it just wasn't working right. And really, what we got to do too is we want to compare this. I don't know why they didn't put my plot format in here. Like I got one. This one should always have final P4, which I don't know why it's not showing up in the file because there should be one. There, no, they P4. I don't know why they did that. So make sure that like the naming is correct. So you can see the total porosity. Now that I fix this, right, the total porosity is matching better. There's still some issues here where I'm too high. There's a lot of dolomite in that clear fork. So that's where I come in again and, you know, I can adjust that a little bit. I can rerun my site program now. I could see that it did, right? I got rid of some of that dolomite, lower the porosity. You're never going to get a perfect match on a lot of this. Some of it has to do with just noise too, and the inability of these tools to read some of this fine grained rock properly. But for the most part, not bad, right? And then once you've done this, you know, I would definitely, and when I see things like this too, by the way, I see this like edgy, blocky shit. This is oftentimes due to some sort of problem with depth offset data. Because why would it, you know, why would it do it like that? I mean, look what's happening. You got dolomite, and then the neutron goes down, density goes up, and then you get lime, and then it puts dolomite back in. Like something's clearly wrong there with the raw data, but we can't afford to fix all of this and just take forever. kind of fix it a little bit. But again, you got to watch what's happening here. So if I look at the trends, I see the Wolfcamp C, for example. Now maybe it would benefit me from moving that endpoint back up a little bit. So it kind of helped me there. And then the Wolfcamp D, same thing, maybe move that up a little bit again. Help me there, right? Then I get that dolomite back in. So we see that there's been some core plugs taken, and like here in particular, they don't see any dolomite, but they're sampling in between some of these stringers that we've got. So we've got this trade-off that's happening now between the total porosity, right, and the grain density on these things. So if I go back to these and I say, okay, I don't believe that anymore, I'm going to go back down to here, and I'm going to extend my neutron endpoint out further and rerun this. I managed to wipe out the dolomite and maintain a lower porosity, right? And the way I did that was I moved the neutron out further. So it's absorbing some of that. I can do the same thing with the A and the B here. I'm too high on porosity. I've got dolomite. I'll bring that down, but I'll bring it out to like a 0.6. Boom. No. And if it's a problem, where the hell am I? If it's a problem just with the porosity being too high too, then I can always move it back up. But then I get more of that dolomite back. So we know there's a little bit of dolomite in there because we see that little spike there, you know. So I'm not too terribly concerned about this. I think that's fine. This lower Sprayberry shale I'm worried about. That doesn't look right at all. A similar thing where I've got the porosity's high. What if I extend that out to like a 0.6? Got something weird going on here with our clays. Porosity's fine, mineralogy's better. So it's kind of like, you know, you come in here and you look at the endpoint. Normally we're at a 0.42, 52 or whatever. Like everyone is kind of just screaming like, put a 0.6 in there and see what happens. Why? Different part of the basin. The neutron curve could be off. You know, just could be that simple. There you go, right? Put a 0.6 in, porosity matches. And if you really wanted to know, let's have a look at that because they didn't necessarily normalize some of these things. So could it be that the neutron's off? It turns out that these wells are actually not that far apart from each other. So I can grab, you know, the 7H well, wherever that thing is. See how we do this. There's a 7H. The other one's. So yeah, it does. Let's look, right? Let's continue to look. So we're over here in Howard County. Yeah, Ackerley Nichols, you got the 7H, you got this black goldeneye. Let's pull him in there too. And have a look at that one. I can find it. There he is. So we've got 3 wells now in the same area. And the other thing that we have to do is we need to be very careful about, that's going to be a shitty mess if we do it that way. But we need to be careful that, you know, the black golden eye and everything is in the same interval. So if we just kind of eyeball this, it's like 5,000 feet to 10,000 feet, let's just say, right? So if we can find everything in the massive list of shit, there's 5,000 to 10,000, 5,000 to 10,000. 7H is missing data, and 5,000 to 10,000. Yeah, what is it complaining about? As an invalid depth range. Whatever. So that means the 7H well, because it's missing some of that stuff to look at it, missing Clear Fork and all the stuff above. So forget about him. These are the two you need to keep an eye on. And you can see that the neutron's higher in the well that we're having problems with. So, how do you, I could go through this exercise. I'm not going to waste the time where, yeah, I normalize it. I bring it in here. I redo all my clay computations without having to change that 0.6. And then I get a better answer. That's the right way to do it. And you chalk it up as fucked up data that needed to be normalized. But, outside of doing that, essentially that's what's happening, right? And I'm punching this up higher to compensate for the fact that the neutron needs to be normalized. You'll see this in some of these wells, something's fucking wrong. I'll show you another example. So I'll save this one too as is. You can come back in and play with it later or something. I want to show you the Jones-Holton here. I'll pull it up over here. So I did, and this is how I'm learning more about this too from the software now. We've got this mineral inversion module where I can run it as a solver, and it's showing me where like some of the wells have good fits and some of them don't, and like where are the fits good, where are the mineralogies off, what that's helping identify some of these problems too. Like here's another one, Ellenberger. That's the mineral solver model. That's actually right. Our model is wrong because it's putting quartz in there and shouldn't be, type of thing. But this is what I wanted to show you. I think it's, yeah. So this well, if you look at it, all this assisted history matching, core data, everything else, the porosity from IP is just high across the board. The whole fucking thing is high. And there's dolomite in it. So why is it high is the question. So let's look. Let's find out. Jones-Holton 49. Why are you high? And guess what else we have in this well? We have ECS. So I have calcite. Oh, I'm sorry. Boom. I've got clay. I've got QFM. I've got calcite. This guy is already 0 to 1. This guy needs to be changed from 0 to 1. And this one needs to be changed from 0 to 0.5. So now, again, not that this is the ultimate answer to anything, but use it as a guide. So I can look at this a couple ways. My lime volume is pretty much on. My QFM volume is pretty much on. My clay volume, which their clay interpretations are a bit off sometimes, it says I need to have a lot more clay in this upper zone than I do. But, maybe that's the case. Maybe that's not the case. I mean, it's not, it's 25%, right? So not having the clay could explain a lot of this. I got too little clay. Okay, fair enough. So let's look at the clay. Wow, what a fucking mess this is. So that, I think, these are very heavily set. Maybe too much so by someone that was trying to get rid of the quote. So the other thing I see is that across the board, the Sonic is just fucked up. All the way down to here at least. So we need to change that, sure. And that's one of the ways that we can do this is trying to get that to align better. I'm still, my Sonic's got, probably needs to go over here or something, or even more. Like, who knows what the quality of this data is. But, okay, so Sonic's not throttling me anymore. The rest of this stuff, I don't know. I had one of these open, didn't I? Are you closed? Fucker. Like strong, interesting stuff going on down here, right? And certainly here, this is fucked up. Like, you see this often where, okay, I need to open that up. I need to move my matrix endpoint a little bit to de-throttle it on the bottom end. And then gamma ray, I don't know why we put 15s in there. But that'll clean that up. And here for sonic density for the Wolfman, let's see it, zone 10D. Like I'm gonna change that to 130. Drop that down. Okay, so what if I just run this simple sort of take on this? Changed it already. And now we need to put something as a benchmark against that. So trying to think, I don't think we have. I'll just run that program. Okay. And then it's gonna fucking reset my things. Probably sure as fuck it did. The fucking most annoying bug in the world. I don't refill that shit out every time. Okay, so now at least we've got something that we can go on for our total porosity and see. So it matches almost perfectly. Okay. And what we really need now need to pull this in to kind of see. This was the 49, right? I'm gonna dump just VT. Okay. From wrong block. Jones Holton. Both of these were exported at the same time, and ours too. So I'll drop this in here. The Z jump set. Okay, now I've got the actual PT curve from, let's see how much different it is from what we just did from the thing. So it's still lower, right? But not significantly so. Like it's not as bad as it was before, just a little bit lower. So just by doing what we did, by tweaking some of that stuff, we fixed this, mostly. And if you look at the calibration data, it still isn't bad. And there's, need to copy all the rest of the plots. And so there's the core data. Oops. So saturations and porosities, everything is sort of lined up on this thing. The dolomite volumes are a bit high, and the TOC volumes are a bit low. And those are sort of like mutually exclusive. I think it's a sampling issue. I mean, you do have some dolomite values here that get kind of high. This is a big carbonate debris flow that could be dolomitized, so it kind of makes sense. This stuff down here is the Barnett Shale. This is all fucked up, but again, do we really care about that? Because we're looking at the tops and the L, and we're not counting that now. But we need to get the stuff correct, because the whole point is we want to do more of this stuff. We're running this inversion and we're looking at machine learning stuff. This has to be clean. The interpretations have to be clean. Otherwise, there's no point. Clean data. So I'll save this well too, right? But what I want you to do is go through here and play with this. I think you've got a link to this database, right? ML project. Okay. I'm going to close all these wells. I've saved the ones that we worked on, right? Already, I'll save that one too. There's only 3 of them we did. But it's out there. There's a link to it. I'll send it to you. You can export this into PetroRes Studio too if you want. But back to this thing. So now this thing, what I've done, I'm working on some more stuff yet, but the whole idea is you pick wells, you pick the curves that are input logs, and then you pick the curves that you want to use to train. And these necessarily don't all have to be log curves. These could be core as well. So like, for example, maybe I want to use the core saturation data instead of the interpreted one. And then, you can train this model. You hit the plan button, it'll tell you all about how many sweeps and all that stuff. But you can train it to sort of take these ones that aren't locked, and it'll, even by zone here too, it'll go through and figure out all the clay parameters. It'll figure out clay bound water volumes. It'll figure out anything that you don't want. You want it locked, then you lock it. Right, I come in here, I can say clay bound water. I'm not going to fuck with that. I don't know enough about it. I'm going to leave it alone. I'm going to set it at 0.15, and that's that. That's what I would do. I'd come in here, seat it at 1.5, lock it through every formation. Don't need to worry about it. My fluid density, that should be, for example, that's 1.03. It should be that way for everyone. I don't know how that one formation, a whole bunch of formations got unlocked. Now they're all locked. Like at no point should we be changing the fluid density, that's the same. Fluid for neutron, you can change because that's something that's used to compute the clay differences. Fluid for DTC also needs to change in order to do the clay analysis. Neutron for the matrix can change a little bit within the low and high that I've given it. So I say matrix can go from negative 0.05, which really that should be negative 0.04, or no, 0.02, right? Negative 0.0, well, I'll give it a little bit. 0.03. And then the high side is that 0.008, which would be dolomite. Seems like this parameter set got fucked up somehow. I don't know how it happened, but it did. 2.87 for that on the high side for, I'll even put in 2.9. What the hell for the matrix density? TOC on the high side. If you want to allow a multiplier, I think I got that one locked. Should be locked for all of them. I don't want to do that. Gamma ray clean, I don't want to mess with. Like on this thing here, you know, what's the lowest possible clay density I could have? 2.52 or something. I don't know. What's the possible lowest clay neutron? I'll put 0.5. What's the clay DTC? 115 on the low side, right? CBW 0.1. RW should be 0.04. TOC multiplier, I don't care because I'm not using it. Matrix density on the low side, 2.65. Very low, possible. Okay, all the rest of this stuff looks like it's consistent. Fluid density, again, I don't know why that keeps getting fucked with. Fluid on the neutron on the low side, I'll put 0.6, just because I know it's going to move it. And I'll put on the fluid DTC side 150 because it's moving that for clay. Okay, and then the high side for the clay, 2.7. For the neutron, 0.6. For the DTC, 130. Or whatever, that's fine. That's locked anyway. Gamma ray, we'll put 500. Clay bound water, 0.15. RW, 0.15. That's fine. This I will change to 2.88 or something, I guess. We already changed that. Matrix DTC, fluid density should not be anything other than that. Don't know why that keeps changing. This should also be nothing greater than 1.03, and that should never be greater than 189. Okay, so I got what I got locked. Just gonna check these again, make sure the software didn't fuck something up. Nope, they're all filled out properly. My seeds, leave them where they are, change them if you want, whatever. Definitely gonna change gamma ray clean to 0 for all of those. And then you can mess with the rest of the parameters here. So PE somewhere in that range for clay. QFM, that's fine. I'll leave that. The neutron, I'm not going to fuck with though. I'm going to leave the neutron at what it is. I'm not going to move the matrix endpoint for the mineral. The PE, I'll let it change. The DT, I'll let it change. Gamma ray, whatever. Do all that for all the rest of the minerals. Pyrite, I'm locking in the relationship that we've got. I'm not allowing for it to change the pyrite volumes. POC, I am. I'm allowing it to change the entire formulation of this. However, I am capping it. Cap it at like 15% max TOC, nothing greater than that. These are all gates. DRO, I'm fixing that. That's a single relationship for all wells. And then I'm floating the M's and the N's, but I'm clamping the intercepts and I'm clamping the maximum and minimum values. So it has to be between 1.5 and 3. It can't be any greater than that. Can't be any less. I never fuck with tortuosity, the A and Archie's equation. Now, the other thing that you can do is when you run this, you can weight these different inputs, just like a reservoir simulator, right? So I want it to nail porosity, saturation, and TOC and clay. Like those are the 4 things. I weight them equally. Go, right? If I want to do core data, I have to check this core button here, and then you tell it that it's core by doing something like that. Otherwise, it just kind of it just assumes it's logs. So for the solver, you can put your mouse over some of these things, and it'll tell you what they do. Right? There's a nonlinear aspect to PE. So one of the ways of dealing with that is with an outer solve. This thing I was playing with, but doesn't seem to be as good as the solver that we've currently got. For the most part, leave all this stuff alone. So if I come back to this now, it says, look, I got to do 2392, which is about 3,000. I could save this configuration file. I'm going to do that. I'm going to call it fixed seed with tube. Okay, done. Then I'm going to train it. So what it does, this here, hold on, let me cancel that. I did it on too many wells. We're going to do it on this Jones-Holton well. It takes a long time to cancel because it spools up of every core on the machine to do all this stuff and grabs all the data. So. But what I'm adding right now, or in the process of adding, is like some additional constraints that we can add. Like in other words, it's it spits out a report when it's done too. But the constraints are going to be around, like here, I'll show you an example. You come into Mineral Solver. One of the things that you can do in the model is you can select something here in this equation bit. And you'll see that it, like I've got unity, okay, that's volumetric unity. Everything has to add up to 1. I've got density, I've got neutron, I've got sonic. Those are equations for density and neutron and sonic. Okay, if you come back over to this thing and you hit equations, those are the equations. Here's the equations, right? Density must be a function that is whatever the density of the clay is times the volume of the clay plus the density of the sand times the volume. You know, it's very simple. You're just summing up all your components and they're equal to your density, right? That's what that is. And if you look at it, there's a density that and the volume of clay, there's a density and volume of quartz, there's blah, 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 blah. It makes sense now, right? This is exactly the same as this. But you've got other things in here. Like you've got these things that are called constants. You've got linear. Okay. So linear, for example, this is a y equals mx plus b type of thing. I can make one input a function of another one. So I'm trying to do the same thing here. I'm trying to set the matrix up for the solver so that we can impose things such as, for example, I know that the n, right, Archie's n of TOC, the saturation exponent, must be greater in TOC rich rock than in quartz rich rock. It must be, because it's affected by wettability and TOC is inherently oil wet. So this should be a 10. That should be a 2. The solver, however, has no constraints. It only knows what the range I give it is. So it says anywhere between 1 and 10, I could find a solution. But if I set a constraint on the parameters that says this value must be greater than the other ones, then it forces it to only solve where that happens. You know what I mean? So we can do that for a lot of these things. We can say, you know, this got to be greater than that. Calcite and dolomite must be greater than QFM. You know, BRO must be a function of some other things. We can set up multiple functions inside of the system itself. But here, let me show you what happens. So we'll pick that Jones-Holton 49. And now we'll train it with 3,000 runs. So it's going to show you now, and I hope this is, you know, that this is something that you're excited about, because you got me thinking about mineral solvers and the fact that I haven't really built one yet, and I've been using these things for years, and I know all the fucking problems with them. So, I'm really excited about this, to be able to actually start solving the solver. You know what I mean? Instead of just having to punch values in there and hoping that you're getting the right answer. Now we're actually getting the right answer through inversion. So the way this works underneath the hood, I'll show you when the report pops, is that it changes all the parameters to a certain degree, and you'll see it's like flying right now through a lot of these runs, because it kind of messes with the extreme endpoints on some of the end parameters, and it sees if that parameter changed the result substantially or not. If it doesn't, then it kind of flags it as non-important and then doesn't bother with it anymore. So that reduces the number of runs that you make. You know what I mean? And it only accepts a run if it improved the answer. So you see, like, sometimes in this this misfit thing is, it's okay. So now it's done. So it spits out a report for me, tells me important information about what happened. It says, I actually managed to reduce the fit on this well quite a bit. Took me 2 minutes. Here's how it was configured. Input logs, calibration targets, right? Gives me some information about how the solver was set up. And then it tells me before and after fit on some of the parameters, like clay got significantly better, dolomite got significantly better, saturation uncertainty, stuff like that, right? Mixed trajectory. And then it tells you about the parameters. So it says, okay, what moved, what railed. It hit a wall on the far side and just stuck there. But quite a few of these things move, and the pay rate has got to do with how much change you got out of it. So a lot of these, it orders them kind of by the higher pay rate stuff. But like, wow, a lot of things going on here. Now, if I go back and look at what happened, this is now my interpretation. Whereas before, my porosity was way high, right? Way higher than what I had. Now, basically, I've matched exactly what came out of IP. I've got more dolomite, I've got lower porosity, and I achieved that because if you look at what ended up happening, is it changed the clay endpoints the same way that we did it. We went in there and messed with them. It messed with them, found the same answer that we did when we did it by hand, and everything else matches. So interesting, if that's what you get. So cool stuff, And if you look at the M curve that comes out on the far right, anything less than 2 is yellow, anything greater than 2 is blue. So I see, like, the carbonate is a high M. I expect that. My sands, my Sprayberry is a low. Shale high, good. Joe Mill low, good. Lower Sprayberry high, good. Dean low, good. Right? This shit in the Wolfcamp C is low, but there's a reason for that. It's because that's highly conductive clay, I can see my vitronite reflectance data sitting over the top of the curve. It's matched. Porosities, all the core data matches. Like, this is a good match. This model is a good model. And what you could do is you can save this then, and you can run it deterministically on any other well. So the idea is that we solve these 72 wells together and find one single answer that satisfies all of them for the parameters. And then that's the model that we use. Problem with that is we can't do it unless we fix all these wells up. Yeah. So good project for you, right? It gets you a lot of experience quickly in sort of evaluating the well from a QC standpoint. So yeah, dig into this database, start going through some of these, play with the data as well.
And that's the other thing, like if we're going to train to core data, we need to clean all the core data up. And the way that I've been doing this is I've been copying certain data into a core final set, but you'll see that there's all kinds of other data in the core sets. And you know, some of it comes from multiple sources in a single well. There could be rotary sidewall cores plus a whole core. Like this bottom section could have been a whole core, and this upper section rotary sidewalls. Different types of analysis. This could have been routine core analysis. This stuff could have been unconventional GRI. And if you look at the problem, it's this. Very, very clearly is this. You know, when I'm fitting data, when you click that box over on the left, what that box does is it upscales some of the core data so that, you know, you blur it over more than a foot and a half of a foot. But you got shit like this. And no matter what you do, you're never going to match that. And that's noise. And it's a sampling resolution problem, right? And so what we need to do is create another set over here. Instead of core final, we have like a core final 2. And we copy all the data, but we remove some of these points that are going to cause us problems in our matching process. You know, like this stuff here too, like never going to match those points. I just got to get rid of them. That one too. And then by doing so, when we go to do the core match, it'll look a lot better. Because right now when we do that, and I'll show you. Let's just do that here real quick. So if I come in here and I say, I'm going to point this to my core saturation. Instead, I'll say that, condition the core, upscale it to 4 feet, fuck it, right? And then retrain this thing. And what we'll do, because we're tricky, I've been doing this already. Wrong window. Oh, wrong window. Ah, right window. Is we're going to put a screenshot. And so there's a little screenshot button on here. It looks like that one right there. You just click that. Here, let me fit it first. There's the whole well. I'm going to screenshot it. I'll drop it in. There it is. So we'll say this one is trained to MSOL curves only. This thing runs pretty quick, right? I mean, not bad for one well, like thousands of simulations. There's also a Monte Carlo simulator on top of this in here. So once you get a model tuned, you're like, this is it. These are the parameters. Then you can set uncertainties around those parameters and run Monte Carlo where you can specify how many simulation draws it pulls and then give you uncertainty bands on all the computations. And that is super fucking cool. And I've never seen that anywhere. So we might be the only ones with that. And what I want to do, like it follows the chain all the way through these equations, you know. So like I changed my vitrinite reflectance profile. That's the only thing I change. I leave everything else the same, right? I just change my vitrinite reflectance, and I can run a Monte Carlo sensitivity against how much that impacts my total porosity. All the rest of the computations are in the chain, right? It's using the different density. It's using all these things. And that's so fucking cool. Because then you can say, this is what I have to worry about, and this is what I don't have to worry about. All right. So now it did the saturation thing, came through. I'm going to bypass that report. This is what it looks like. Everything else is kind of the same. If you look at it, saturation's changed. The M and N changed. Everything else is the same. If I screenshot that and I drop it in a plot and then hammer it, now I go back and forth. Look at what happened. TOC is changing too, by the way. But really the biggest drivers on this match was M and N from Archie. That's exactly kind of what I would expect to happen. This is sort of an uncertainty too, because, you know, we don't have saturations everywhere. Anyways, what I'm hoping to get out of this, I'll put this one train to S24. What I'm hoping to get out of this is, you know, more information about these unknowns that we don't have electrical property measurements, you know. Now, I'm also trying to improve TOC as well because uh, you can see TOC is higher in this case, it's lower in this case. And I think like the Joe Mill, this gate, this yellow or this orange curve is a gate. What that gate does is it's a multiplier on top of the TOC that we got. So if it goes low, you can see what happened. Like the red curve is what's computed from our mineral solver or from our multi-line equation in IP, and the white curve is the new one. So what it's done is it zeroed this shit out based off of mineralogy and stuff with this gate. Correctly so. Like these are clean sands in the Joe Mill. Once we clean up the problems that we saw with the neutron and everything, we'll get rid of that dolomite. But anyhow, stuff to play with, right? And I think a lot of meaningful papers to be published here, a lot of incredible work to do. It's just going to be a difficulty to get, you know, data to publish unless we do it with Diamondback or whatever, which is possible. But it also changes the game completely, if you ask me, because, you know, up until now, everything has always been this sort of world where you're an IP, and if you look at the way QEP did stuff too, they've got like 14 or 15 different models in Mineral Solver, right? Like you load one of these wells, there'd be 15 of these things. Model 1 through 15, one for each different zone would get a different model with different endpoints and shit. So I didn't like that because I started putting parameters in for curves. So I just use one model and let the curve change, right? Instead of hard-coded values. But still, there's even a better way to do it. That's with this sort of approach. And then two, you get these equations. So I get the equations for, you know, the gates for the TOC. I get my M and my N equations out of this to use to reconstruct everything. If I change my TOC equation, I get the new equation there. So, you know, once this is done, you can run it deterministically on any well. And, you know, I don't have to go in. I've got best guesses now for my clay and everything. I mean, I spend so much fucking time every time I come into a well. I'm sure you do as well. Setting all the clay endpoints and playing with that, right? This totally solves that problem because it's already got them populated. You may need to tweak them a little bit, right? But it should be pretty damn on already done. So I will. Where are we at? We are here. ML project. Copy link. I'll put it in the chat here. So yeah, what I'd like you to do is go into these wells. There's 72 of them. Some of them are going to be totally fine. Some of them are not. But have a look at them. See if you can find ones that have problems like the Jones Holton that we just looked at or these other ones. You'll see the weird stuff going on. And I want you to do this for multiple reasons. One is I want you to play with the core data a little bit and the ECS data and the NMR data and start to get comfortable with those types of data that you've probably not worked with before. And get comfortable with how, you know, all the interpretation stuff works inside of IP and kind of changing the interpretations and seeing how all of those things are tied together and work together. And then, we'll go from there. But just remember, we're only interested in the tops underscore ML intervals. If it's not part of that, we don't mess with it. If you got any questions, don't sit on them. Just make sure you ask me right away. When you're finished with this, you should have a really good understanding of petrophysics and how we're doing this. And the core data, if you have any questions at all along the way, just send me notes. And I'll tell you, to the best of my knowledge, how that data was recorded. Like we talked about some of the stuff earlier, right? Like looking at the total volumes, adding up the saturations, and how there was a mismatch, stuff like that. Kind of key, because if we correct that, it gets our saturations more accurate. So we don't want to calibrate our models to shit, We want to have the right answer. And for the motif thing, I talked to Corey. We're gonna wait for continue doing what you're doing on that as well if you've got time. And we're waiting on Calvin to kind of get back to us with some feedback. They're looking at the results from the first pass. And once we hear back from them, then we'll worry about a second pass. And what else? From that meeting. I didn't write any notes down. Bad on me. I think that's about it, really. But keep playing too with the Claude and the software. And one last thing, so some of the changes that I've done have all been like today and yesterday. So if you want this latest version in your source code base, what you'll need to do is tell Claude to pull everything from the master branch and merge it into your branch, not the other way around, but pull from master and merge into your branch, and it'll grab all the stuff. And it should be no conflict with what you've been working on potentially. So. But again, like when you're playing with this as well, think about it. If if you've got any ideas, let's talk about it. Because you probably have used reservoir simulation software and stuff more recently than I have that's newer. Like I can't even remember the last time I ran a CMOS model. It's been years. And I don't play with TNAV or any of these other newer generation things. So, different ways to set these problems up and solve them, but ultimately we constrain the answers and we train it on a big enough data set of good data. We should end up with a really good model. All right. Any questions? You good? Okay, well, go ahead and play, and like I say, poke me if you have any questions or you need anything. Yeah, cool. All right, talk to you later. Yeah, bye-bye.